All right, so we are continuing on section 4.5, and the next topic is concavity. All right, so what in the world is concavity? I already made a couple of references to this concavity. It has to do with whether you are steering your car to the right or to the left. All right. Also related to this idea is points of inflection. Now, people use this metaphorically. Maybe I'll mention this again, but when things like a political outlook or economic outlooks are changing or something, they say this is a point of inflection or this is an inflection point, and it's an appropriate use of the term because this is when concavity changes. All right, but first let's start with this definition. Because we need to define what this word means, concavity. All right, so suppose f is differentiable, which means the derivative exists, differentiable on an interval. Okay, I don't specify if it's closed or open. All right, and then if f prime is increasing, all right, remember, I'm not saying if f is increasing, I'm saying if f prime is increasing on this interval, then f is said to be concave up. All right, and the idea is, basically it's going like this. Okay, now it could be, maybe I should say it's like this. Any part of this function that looks like this is concave up. All right, now if f prime is decreasing, that means the amount of the rate of increase is decreasing, if you can understand that, and you should, then f is concave down. And for this, you should imagine this picture. All right, so one is driving to the right, one is driving to the left. Okay, that's the idea. All right, now concave up. Oh, sorry. This is something's wrong here. If f prime is increasing and if f prime is decreasing, then these function, the first one function is concave up, second one concave down. All right, so you have this function that looks like this. Okay, so this is where f prime is positive, f double prime is positive. So this is concave up. Okay, and you can also have an increasing function, but here, as I said before, the derivative is positive, but the second derivative is negative. Right? And the idea is if you are to draw these tangent lines, they are always to the right if the function is concave up. And if you take these derivative arrows, they are always going to be on the left if it's concave down. Right? So again, that's the idea. And of course, if here's a decreasing function, this is still concave up. I hope you can see that. As long as you're turning or steering your steering wheel to the left, that's concave up. So here, function is decreasing, but the derivative is increasing. And then you could also have concave down and decreasing. So this will be the derivative is negative, and the second derivative is also negative. Okay, so this is actually not too difficult, but what happens if concavity changes? So if concavity changes in an increasing function, it could be like from this. Okay, so the function is still increasing, right? Or you could be going like this. Both of these cases, the function is continuously going up, increasing, but the this is going from concave down to concave up. So the derivative here, the second derivative is negative, and then over here, the second derivative is positive. So guess what happens to the second derivative here? Yeah, it's 0, okay? So here, concave up to concave down. So this is up to down. In both of these, the function is continuously increasing, right? So this is down, right? Again, at this point, you have the second derivative going to 0. Now, if you're going down, you could have this kind of decreasing function where the concavity is down and 0 and then goes up Or you could go this way, again, decreasing, but concavity is up here, concavity is down, and each of these has a point that I'm indicating where the concavity changes. That leads to our second definition in this subsection of 4.5. If F is continuous at A, and if F changes its concavity, and this is this covers both directions, up to down or to down to up. If F changes its concavity at A, then that point on the graph A comma F of A is called a, and here's the term I'm defining, a point of inflection. Some books will call this an inflection point. Same thing, of course, of F. Okay, so make sure it's continuous. So in other words, it doesn't look like this. So this is down and this is up. This is not, which point is that? Well, neither of these points is called a point of inflection. The function has to be continuous, doesn't have to be differentiable. But anyway, okay, so that is what we mean by this. Now, roughly speaking, I have mentioned this before, but a point of inflection is where you change the direction in which you are steering your car or bicycle or whatever you drive. Okay, if you go from, see here, you're driving and you're steering to the right, and at this point you start to steer at left. Okay, so just so you know, here's the interstate, and this is, well, some of you may actually do something similar to this. You have this road, and when I used to go home, you would be driving here, and then there's a left turn, but that is to go to join this interstate. Okay, this is, let's say this is Interstate 5 going north, and here is your street. Maybe this is called Valencia Street or something, Valencia Boulevard. So in order to go I-5 north from this campus, I have to drive this way, and I have to go left in order to turn right onto I-5 north. All right, so do you see an inflection point here? Yeah, because as I start to go to this ramp, I have to turn left, right? Somewhere right here, somewhere around here, I have to eventually start steering to the right. This is our inflection point. There should be a sign, a traffic sign, say, hey, this is an inflection point, but they don't have that. Maybe I'll install one. Okay, but the point is, if A, well, let's say if A, FA is a point of inflection. I should say this as a fact or a theorem. Then the second derivative is 0 at that point. Actually, it could be undefined, right? So look for a critical point of the second derivative in order to find the point of inflection. It's not as hard as it may sound. Here's another example of this. X cubed, well, here's the first example of this. This is similar to another example we considered earlier, the polynomial function of degree 3 that says x cubed minus 6x squared plus 9x plus 30. Okay, let's find points of inflection. Okay. By the way, the first derivative of a cubic function is going to be a square function. The second derivative is at most a linear function, right? First degree. So, and how many zeros does a first degree polynomial have? Basically 1, okay? So you know that if you have points of inflection, there's only one of them. And that's something you know from the way the degrees of polynomials behave. All right, let's try to find the derivative. 3x squared minus 12x plus 9. It looks familiar, right? So from here, if you factor out 3, and if you factor the rest of and set that equal to 0, you can make a little table, a sign chart, and you can figure out where the function is increasing or decreasing. Maybe I'll do that later. Okay, but here we are looking for the second derivative, and where the second derivative is equal to 0. So it's 6x minus 12, right? And you can set this equal to 0. Of course, x is equal to 2. And so this is possibly an inflection point. Now, it doesn't have to be. Okay, what I said here is if you have an inflection point, the second derivative is 0 or undefined. Just because the second derivative is 0 does not mean that it's a point of inflection. Okay, here's well, let's see. You have x to the fourth. Then this turns out to be where the first derivative and the second derivative are both equal to 0, but it is not a point of inflection because it's concave up, concavity doesn't change, right? So you have to be careful to not to assume the converse of this statement, the fact that I stated. All right, so what happens at 2? So you could actually do this sign chart also. The second derivative is 6x minus 12. Before 2, when x is less than 2, this is negative. When x is 2, that's 0. When x is bigger than 2, that's positive. All right, so that means it's concave down here. I can't spell down. All right, so this is concave down, and this is concave up. Now, this is all we know. Okay, we don't know yet if it's increasing or decreasing, right? So in order to, so this will show the concavity. And by the way, this shows, therefore, based on this, okay, we know that x is equal to 2, or you could say f has an inflection point or point of inflection when x is equal to 2. Now, you would have to evaluate this at 2 in order to find out exactly what that inflection point is on the graph, but you do know that there is a point of inflection when x is equal to 2. All right, so in order to graph this and determine the overall shape of this graph, the graph of this function, let's consider this the first derivative where we factor out 3, and this is after you factor out 3, you can factor more. You can do 1 and 3. Okay, and you can set this equal to 0. That tells you x is either 1 or 3, right? So something is happening when x is 1 or 3, and so maybe we can do a sign chart. Okay, you have 1 and 3. So now dividing the entire real line into 3 parts: negative infinity to 1, 1 to 3, and then 3 to infinity, right? So here, let's do x minus 1 times 3, okay, because you have the 3 there. And so we can do a sign chart. When x is less than 1, such as 0, this is negative, and then 0, positive, positive, positive. Remember, my own way of doing this is not only do I put the sign in each of these intervals, I like to put either 0 or positive or negative right at these points, okay, the critical points. X minus 3 is negative here, plug in numbers, any number between 1 and 3, this is still negative. I mean, it's obvious because any number less than 3 is going to cause this to be negative, right? And then this is 0 and positive. Now the combination, the product of these is the derivative of f. So this will be positive, 0, negative, 0, positive. And as I said before, I would like personally to visualize what's happening with the graph. So I go up, 0, down, 0, up, like this. Okay, now we know a lot about this function. For instance, we know f is increasing from negative infinity to 1 union 3 to infinity. It's decreasing on the open interval from 1 to 3. Okay, so while we don't know exact, I mean, you have to plug in some numbers in here, right, in order to calculate and figure out exactly what the graph looks like. But But we could sort of figure out what happens to this function. All right, so this is 1 and this is 3, right? What we know is that the function will be increasing up to 1, going down here and increasing from 3 to infinity. And there is an inflection point at 2, right? So when x is 2, then we have an inflection point. Now, it would be helpful if we know what the value of these functions, this function is at these points. Okay, so I'm not going to do a careful graphing of this, but I'll just go ahead and sketch this. What's going to happen is when x is equal to 2. Oh, by the way, when x is 0, you know, the value is easy to find. It's, you know, because x is 0, f of 0 must be 30. That's the y-intercept. Now, you know that the function is still increasing at this point, right? And in fact, concavity is down and increasing. So the graph must go like this up until 1. Okay, remember, it's a concave down up until 2. And then after 1, concavity is down and the derivative is negative. So it goes down to some point. Okay, and at 2, what happens? Well, from 2 to 3, the derivative is negative, so it still goes down, but concavity changes right here. So we have an inflection point. So you start to steer to the left, and then, oh, oops, that doesn't go like that. It hits the bottom, the local minimum at 3, as this indicates right here, and then starts to go up again, right? So you can see concavity is down here, and concavity is up after 2, concavity up, right? But the function is increasing up until 1, and then from 1 to 3, it's decreasing, and then it increases again. So while I don't know what this point is, I don't know what the value is at 3 or 2 or 1. You can easily calculate these values, but I do know that overall the graph is going to look like this. And of course, the end behavior is correct. You know, the cubic function with a leading coefficient that's positive is going to look like this, right? So that is a rough sketch of this graph. And we got the concavity right. We have the local minimum and local maximum right. There are no other local extrema. And so this is what the graph looks like. All right, cool. This is how much you can do with the derivative and the second derivative. All right, so you have seen the importance of studying the second derivative and concavity. And now with this, okay, so for instance, if you look at this point 1, right, that's where the maximum happens. But if you look at the second derivative, the boundary point was 2, okay? At 2, you know, the concavity changes, right? So here the concavity is down, concavity is up. So what happens at these two critical points? If the critical point, you know, here's a critical point 1, here's another critical point 3, but at 1, concavity was down. And that seems to be indicating that you have a maximum, okay? And concavity is up here, and you have the derivative 0. That seems to indicate that it's a local minimum. And that fact is the topic of the last part of this video for section 4.5, and it's called the second derivative test. And we will cover that in the last part of